everyone can see that?
Yeah, that's fine.
Very good. So yeah, it's my pleasure to tell you today about our progress with the Vera Rubin Observatory. I'm going to start by describing some of our scientific goals, in particular a little bit about what we hope to do in studying dark energy. That's where my own scientific interests lie. I noticed the talk you're going to have from Catherine Hyman's later in the spring will almost certainly cover similar territory. Then I'll spend the remainder of the talk, the bulk of the talk, giving you an introduction to the observatory, with particular focus on the camera, which is a remarkable instrument that we are building at SLAC, and I'm the scientist leading the construction and integration of the camera. Then I'll spend the remainder of the talk. Okay. All right. So let's see. Very good. So you probably know that around 100 years ago, Edwin Hubble discovered that the universe was expanding. That's Hubble observing on the 100-inch Hooker telescope above Los Angeles. We know now, and Einstein and Friedman learned around the same time as Hubble's discovery, that there were three possibilities for the future of the universe. So the future of that expansion. Either the universe would continue to expand into the future, or the universe would have its expansion stop and then begin contracting in a big crunch, if you will. And of course, there was also the possibility of things being just between those two. And today, we understand that there's even another possibility for the future of the universe, that the expansion would take place in such a way that it would actually rip apart space-time. It's called Big Rip. Although, you know, at that point, you're definitely into the edge of what we really understand about space and time. And for each of these possibilities, the determining factor is actually the density of the universe and what makes up the universe. How much matter, how much radiation, and how much of other things are present in the universe. 20 years ago, or maybe it's 22 years ago now, it was discovered in a study of a certain kind of supernova, type 1a supernova, that the original possibilities that the universe was either going to expand forever or would contract, not correct. And then in fact, yet a different fate of the universe looked like what should occur based on our observations today. That the expansion of the universe is accelerating. And in fact, we don't know, but it could accelerate so fast that the universe would see a big rip, that space-time itself would be affected far into the future. Now this plot shows the original data from two different teams of these type 1a supernovas. And the effect that was observed was that that some subset of those, or that some of those supernova, the most distant ones observed, were a little bit fainter than expected with any of these other possibilities. As you might know, that work led to the awarding of the 2011 Nobel Prize. And today, what we understand is that the universe's composition is mostly dark. There's ordinary matter, the atoms we know and love, making up 5% of the universe, 25%-ish in a different form of matter that is not atoms, dark matter we call it, but that the predominant portion of the universe is actually made of dark energy, an extra component making up almost 70% of the universe, that is the thing that causes the expansion. So it's really remarkable. And I have to say, I spent the first half of my career in experimental particle physics, studying the makeup of matter, and to discover that everything we were studying, quarks, leptons, makes up only 5% of the universe, is really remarkable. And actually, it was for that reason, or partly for that reason, I decided to switch my own research to study the bulk of the universe, the 70% of the universe that we call dark energy. Now, it's worth saying that that name, dark energy, is really just a label, and it's our name for the thing that's causing the expansion, but we really don't know what it is. Now, here's what some of that data, the supernova data on the left, and then results from a number of different data samples on the right combined, tell us today. And actually, these plots are already a couple years old, although things haven't changed much in the intervening time. So the left plot shows, basically, it's the Hubble diagram today in supernova, showing this fantastic agreement with the picture I described, with 70% of the universe made of dark energy. But what we don't know is what's the exact nature of that dark energy. Is it a cosmological constant? In that case, a parameter called W, it's the equation of state, the ratio of pressure to density of this stuff, would be -1, and it would be -1 for all time. But it could be that the thing we call dark energy is more complicated. It could be a quantum field or a modification of general, well, it's supposed to say relativity, general relativity. And in that case, this ratio, W, the equation of state, could be different than -1, or it could change over cosmic time. And the plot on the left is meant to show our current understanding of that parameter W. The measurements are quite consistent with -1, but that's only if we assume that that quantity, W, has always been the same over cosmic time. If we relax that assumption, then our measurements become much worse. And the contours on the right side show how well we know the value of W if we allow it to depend on cosmic time. And A is the expansion parameter. You can think about it as the time parameter here. And in fact, our constraints are poor. We don't really know if this simple picture that dark energy is Einstein's cosmological constant, we don't know if it's correct. You'll probably hear more about that from Catherine Hymans. That is what the project she works on, called KIDS, is working on. I'm actually a member of a competing project called Dark Energy Survey, and we're making measurements today of these quantities, but those measurements are not going to be definitive. And the project that I'm going to tell you about today, the Vera Rubin Observatory, will enable much better set of measurements of dark energy. And we hope to see deviations from this simple picture or not, if they're present. Now, how are we going to do that? Now, to really explain it in detail would take a whole talk, and I'm just going to give you the flavor. One of the ways we're going to study dark energy is by studying gravitational lensing, by looking at how light from distant galaxies is bent on its way to us. Now, this is a picture from the Hubble Space Telescope of a cluster of galaxies. So almost all of the objects here are actually galaxies. But you notice in it these fantastic arcs. These are due to the gravitational bending of light, gravitational lensing we call it, of galaxies that are behind the galaxy cluster. Now, this is a fantastic case, and systems like this, show this spectacular gravitational lensing effect. They're called Einstein rings, in fact. But every galaxy is subject to this effect, where its light will be bent by the matter inhomogeneity between the distant galaxy and us. For most galaxies, that effect is tiny. So instead of producing this fantastic arc, all that might happen is the shape and flux of the galaxy may be changed slightly. And while you can't learn much from an individual galaxy in that case, if you have millions or hundreds of millions, or better yet, billions of galaxies, statistically, you can use that to study how matter is arrayed in the universe. Now, how is matter arrayed in the universe? Well, we can learn a lot from simulations. And this is a simulation and visualization created by some of my colleagues at Stanford. And it shows, starting early in the universe, how clumps of dark matter develop over time. And what you'll see in a simulation like this is just how much fantastic structure is in the universe. The key point for the study of dark energy and the study of the expansion of the universe is that you can use that structure, the inhomogeneity of the universe, to study how the universe has expanded. Let's watch the simulation. So at the very beginning of this simulation, which is just a little bit after the Big Bang, the universe is extremely uniform. But what you observe is that almost, very quickly in the time scale of this simulation, structure develops. Filaments develop, and these clumps, the technical term is actually halo, of matter and dark matter develop. And each one of those clumps is where a galaxy would form. And what forms in the center of this simulation is a galaxy cluster. And so the way that we study dark energy is indirect. It is, since it's not a particle, it doesn't form any kind of structured object. You don't get planets, you don't get stars, you don't get galaxies of dark energy. And there's no known interaction with anything else. It doesn't emit light. The only way to study it is by studying the expansion of the universe more carefully. And so to do that and to study dark energy, here's kind of the inference, here's the chain that we have to make. We have to study as many galaxies as possible over as much of the universe as possible. So because we're after a statistical effect, we need to look at as much of the universe, as much of the sky as possible. We need to go backwards in time, and we need to measure galaxies. That's our probe, is to study galaxies. Then we need to study how the shape and flux of those galaxies has been changed by gravitational lensing. We call it weak lensing because we're looking for only small changes in those properties of galaxies. That lets us map dark matter in the universe. We can make maps that correspond to that, how dark matter is distributed in the universe along the lines of that simulation. And from that, we can infer the history of expansion of the universe, because we'll map out the dark matter at different redshifts, at different points into the past. And only by doing that can we uncover the nature of dark energy. So again, it's a complicated inference that's necessary, and it's highly indirect, but it's really coupled to the fact that dark energy only affects the expansion of the universe. Okay, that sort of serves as the scientific introduction, and this is where my own personal research interests lie, and make up a big part of the driver for the design of the Vera Rubin Observatory. So now I want to switch gears and tell you about the observatory, in particular about the camera that we're building at Stanford. So these are engineering drawings, and the Rubin Observatory is doing a single survey of the sky. And in effect, we're making a color movie of the sky. It's an optical to near-infrared survey that covers the entire southern hemisphere sky to a depth of 27th magnitude. So I hope in an astronomy club, that people are familiar with magnitudes and can appreciate how dim a 27th magnitude object is. Yeah. We'll be imaging the sky multiple times. We aim to do at least 825 times. So that means we'll see every part of the sky that many times over 10 years. We'll do it in 6 filter bands, and our mantra is wide, deep, and fast, as I'll show you. Now, well, actually, before I really dive in, I do want to say something about the name of the observatory. So Up until a year ago or so, we were called LSST, Large Synoptic Survey Telescope. But that name was actually, that's the name only a committee could come up with. And in fact, the name did come up, basically came from a committee. No one really liked that name. And so we decided, well, it was decided by some complicated process to name the observatory for Vera Rubin. Vera Rubin, as you might know, is the astronomer who is best known for developing compelling evidence for dark matter, looking at rotation curves of galaxies, and is really a great person to name our observatory after. I'll still use the word LSST. We use LSST, we decided we would call the survey LSST. It's the Legacy Survey of Space and Time. That name might have come from a committee too. But if I use LSST, you can forgive me, but we're the Vera Rubin Observatory. Now, what do we aim to do? So we want to image the entire visible sky, so the entire southern hemisphere sky. We want to see the sky 825 times over 10 years, means that we want to see the entire visible sky in 3 to 4 nights. So that means you'd see every part of the sky on that cadence. That means we'll be collecting 20 terabytes a night, every night for 10 years. That was a really big number a decade ago, maybe not as scary today. Total data size about 60 petabytes. It's still big data. I said this already, observe every spot in the sky at least 825 times. We think we can do better than that. And for each individual image, our 5 sigma source detection limit, so that's for stars, are between 23rd to 24.8 magnitude, a little bit lower in the Y band. That's in the near infrared, the Y band. In these 6 bands, U, G, R, I, Z, Y. So U is at the UV edge with a mean of around 380 or 400 nanometers. Y is just into the near infrared at a mean of about 900 nanometers. We expect to observe 20 billion galaxies. And the estimate is about 17 billion stars in the Milky Way. We think there'll be something of the order of 6 million solar system objects that we'll observe. If you put those numbers together with 800 to 1,000 observation, that means we'll have a database with 37 trillion objects. That is definitely big data. And actually, all the image data and catalogs will be public to the scientific community in the US with certain foreign partners. And I'll just say a tiny bit at the end, but some fraction of the data will be available to the public, via a special interface that will be created for citizen scientists, for school children, and interested public. Now, in addition to combining the images to see the dimmest objects, and of course, if you're interested in galaxies to 27th magnitude, we'll combine the images, stack them. We'll also use each individual image to find anything that changes in the night sky. And in fact, part of our design is to produce alerts, that's our tech term, alerts that will come out within 60 seconds of the observation, flagging a whole host of objects. So including more mundane things like variable stars, but including supernovas, maybe kilonovas if we see some, to moving objects inside the solar system. And those alerts will also be available. So there'll be a torrent of those, between 1 and 10 million coming out every night, that scientists could follow up with other instruments. So that's an important part of the design, and we think in a lot of ways, LSST or Rubin Observatory will be a finder scope for the entire astronomical community. Now, I said our mantra is wide, fast, and deep. So wide. So we'll see the whole southern hemisphere sky. These are depth maps of using one particular algorithm for how we're going to image, to tile the sky. We take images fast enough that no human observer could direct the telescope. It will actually be done by algorithm. and we'll have an automatically determined set of images to take each night. This shows what our coverage of the sky would look like. You can see there's extra imaging done on the ecliptic and on the galactic plane. Obviously, you don't need to look as deeply on the galactic plane because at some point you hit the confusion limit and more imaging won't help. What do we do each night? So this is one of those simulations. This is actually a somewhat old one, but had been the standard for a while. And this shows how you would take images. So each little hexagon is meant to be the focal plane. And this shows one night of observations. And this night, the images are all being taken in wideband. The moon is up. There's the moon. And then, eventually you get to the next night. And then you decide, let's do G for a while. The dot stops. There are some special spots in the sky where we'll take even more images. And those will be good for supernova, other kind of fast cadence, or fastly developing phenomena. So there'll be some number, I forget if it's 5 or 10 footprints where we'll take even more images than the 825. So why? That's why there's fast, deep. This is a simulation. This is not a real image. This is a simulation of what we think our images will look like at 10-year depth. So, if you've ever seen the Hubble Ultra Deep Field, obviously those images are sharper, much sharper with space-based imagery. The Ultra Deep Field is tiny. So this is of a similar depth to the Ultra Deep Field, obviously not quite the same resolution, but we'll have images like this that cover the entire southern hemisphere sky. That will be spectacular. Okay, let me change again and start to tell you about the telescope and the instrument. And I'll give a little bit of extra emphasis on our design rationale. Why did we build things the way we did? Since we're a survey, since we want to see the entire southern hemisphere sky, speed is important. So the rate at which you can conduct this survey depends on the étendue. That's the phase space of the telescope in some sense. And it's a product of the mirror area times the field of view. There's the mirror on the left after it had been cast, but before it had been figured. This picture is about a dozen years old, actually. So we have a primary mirror, 8.4 meters diameter, and a field of view that is, it's this plus sign shape, but the diameter is 3.5 degrees. So both of those are enormous. To get a telescope that performs well under those conditions is tricky. And we've chosen to go with a 3-mirror design. It's closest to the papers by Paul Baker, but it's a 3-mirror and a stigmat, where the third optical surface, third mirror, removes astigmatism across the giant field of view. And this little inset shows the purely optical performance at the center of the field and at the edge. This is 0.6 arc seconds. The sightseeing contribution will be about this size, 0.6 arc seconds. So this is excellent performance. We stay dominated by the sightseeing. Now, to get a big field of view, you need to go to a fast optical design. So our F number is actually 1.23. That's extremely fast. And it has the advantage that makes the entire structure squat, which is good because we want to slew rapidly. Given that many images, and that will correspond to something like 1,000 images a night, we don't want to waste much time moving from one part of the sky to another. So a squat design will let you move quickly. The other innovation that we've done is to actually combine the primary mirror and the tertiary, the third mirror. So in this diagram, here's the primary, is this annulus. Okay, so it's not really 8.4 meters. There's a big hole cut out of the center. Here's the primary. Here's the secondary. This is an extremely large mirror of this kind, 3.4 meters. And then the tertiary, the third mirror, is actually in the same piece of glass as the primary. Then you go there to the three refractive elements that are part of the camera. And those are needed to do chromatic corrections because we have to have a vacuum window. Okay, now what about the camera? Well, we want a giant field of view, 3.5 degree field of view. That is enormous. But our PSF that we're targeting, or so point spread function, I hope I don't use too much jargon, but maybe you're familiar with that term, point spread function, so that's the delivered C. We expect a full width half max of 0.7 arc seconds. We're obviously at one of the best sites in the world for doing this in Chile. And to get good sampling, we've designed 0.2 arc second pixels at 10 microns. And to cover 3.5 degree field of view, 3.5 degree diameter field of view, that means you need over 3 billion pixels. So that's the largest focal plane ever built for astronomy. And that's what we've achieved. To cover the whole sky in this short period of time, you need fast exposures. We're actually doing pairs of 15-second exposures from the same part of the sky. That's to remove cosmic rays and helps with asteroids. And with 15-second exposures, you don't want to waste much time reading out the images. So we've designed 2-second readout. That is extremely fast. Because of that, we built CCDs with 16 channels. Typical CCDs have 1 or 2. We've had to go to 16 because we need the multiplexing factor to get 2-second readout. It's light for fast slewing. It has a huge number of channels, over 3,000 channels. And because of that, we decided to put all of our readout electronics, so the controller electronics, are in the vacuum, mounted kind of in an integral package with the CCDs. No one has done that before either. We felt it was necessary with this design. The last interesting thing kind of driving the camera design is that with a fast focal system, so at f1.2, the depth of focus is so shallow that the focal plane better be really flat. So we gave ourselves a spec of plus or minus 11 microns for the flatness of the focal plane. We've achieved that, actually. Okay. Here's what the optical throughput looks like. So these are the 6 filter bands, so from 300 to 1100 nanometers. The filters we built, I won't show you any data on those. They're actually half built now. Look superb. Here's the quantum efficiency of the CCDs we've chosen. We have 2 manufacturers. One is actually E2V, which is in England. The other is a company in Arizona. Those look superb. And so I think we're going to have excellent optical properties from our device. In terms of image quality, so these are spot diagrams over the field of view. In each case, let's see. So this is, the seeing disk is the size of these little rectangles. So in all cases across the focal plane, and this is defocused a bit. So inside this whole range, we have excellent optical properties, so excellent image quality. Because we're still dominated by the sea. You could not put this instrument in space, I'm afraid. The contribution from the camera itself, on seeing, is dominated by diffusion. The diffusion is going to be about 0.2 arc seconds. Now, the diffusion is that large because we need to use thick CCDs. They're 100 micron thick CCDs, which are absolutely necessary to get this good performance all the way up to 1,000 nanometers. And this is true of all modern cosmology survey projects, you really need to see light in the red because we're looking at galaxies that are heavily redshifted. And so you want to be able to cover as much of this near infrared edge as possible. Now, of course, you're limited by silicon. You can't go any further than that with silicon technology, but you do want to go here. Previous generation of CCDs cut off much faster in wavelength, and you lost a lot of the important red light in that case. Okay, let me move ahead. Okay, so where do we stand in construction? We have been under construction, major construction, for about 6 years now. and are getting close to the end, which is great. Here's the site. We are at Cerro Pachon in the southern Atacama Desert of Chile. We're on the same ridge as the Gemini South 8-meter telescope and the SOAR 4-meter telescope. So it's a developed site. There's part of a treaty between Chile and the United States on this site. And it has excellent properties. It's dark, it's reasonably high, the weather is good, and the seeing is excellent. So here's the site about, I want to say 8 years ago. There was some pre-construction done where the mountaintop or the ridge top was level. Here's the start of construction of the support building and the dome, and you can see the pier where the telescope will sit. This is about a year ago, showing the building completion with just the work on the dome left. This is this past summer, so southern winter, showing the dome kind of half constructed. Unfortunately, that was work did have to be delayed because of the pandemic. And I'll show you sort of what the dome looks like. No, the pictures from last month. So work has restarted on the mountaintop, so we've made some progress at this point. But you can see we're getting close. Here's the telescope mount. This was built at a company in Spain. This is how it looked at the factory. It was tested in the factory, then it was disassembled. It's all in Chile on the mountaintop, and some pieces of it have now been installed. I forget how much of it is actually installed now, some part of it. Here's the primary mirror. And you can see very clearly the primary part here and the tertiary part here. There's a very large difference in radius of curvature between those two parts. This was figured and polished at the University of Arizona Mirror Lab, Stewart Observatory and Mirror Lab, that has a whole factory of making 8.4 meter diameter mirrors. It's been done for some time, and it's also in Chile. What about the rest of the optics? So here's the secondary mirror, which has been coated now. And then the 3 lenses that are part of the camera structure are shown here. So this package holds the input lens. The second lens, you can't really see, it's underneath. Here it is at its factory. And the third lens is also the vacuum window. This lens, which is 1.55 meters diameter, is the biggest lens ever built for astronomy. And that is sitting in our lab here at Stanford. Okay, let's talk about the focal plane. At 3.2 gigapixel, that's the biggest focal plane ever built. This engineering drawing kind of shows the structure. It's made up of 21 modules, each with 9 CCDs. And the modules hold the controller electronics, and they're a combined mechanical, thermal, electrical, and optical system. Very complicated. Here's one of those assembled here. You can see the 3 readout boards. These are custom boards built at SLAC with a key ASIC built by one of the observatories in Paris, shown. So this by itself is a 144 megapixel camera. All it needs is some voltages, and all the output comes out on 6 fibers. Here's one of the CCDs. They're 16 megapixel, so 4K by 4K CCDs, as I mentioned, with 16 channels. The manufacturers really pushed what they could do in building CCDs with so many channels, designed for fast readout anyway, at 0.5 megahertz, and super flat. Their spec was flat to plus or minus 5 microns. That's not normally what they produce, but they were able to do it for us. Here's 9 of those CCDs arranged in the package. That's facing down in this picture. And here's, I think that's actually me and a colleague looking at our facility to test each one of these units at a time. The cryostat, here's sort of the backside of the cryostat. It's got a lot of equipment in it. It is not a simple device. You can see the bays for the plus-sized focal plane here. There are also 4 special units in the corners that have guider sensors. So 2 CCDs in each corner serve as the guider, so see stars to deliver to the telescope to help guiding. And also 1 CCD that's offset, it's split, offset from the focal plane by 1.5 millimeters to use as a wavefront sensor. And those are in the corners. And here's some pictures of construction. If I direct your attention to this picture here, you might get an inkling of why this was so difficult. To minimize the dead space, the precious space on our focal plane, we wanted to keep dead space to a minimum. The gap between CCDs is at or less than 0.5 millimeter. And the gap between adjacent units, CCDs, is also, the nominal gap is 0.5 millimeter. So to mount this complicated unit, which you can only hold from the back, and we're kind of doing it blindly. You can see the apparatus we built to do it. Here's one being installed. Here's one of our technicians watching it go up. Here's the equipment to visually inspect it and make sure it does not bump into its neighbor. So doing that alone was actually a major effort that took us, we did in kind of 2 steps. Each step took a couple of months. And here's the back of the cryostat with the obligatory rat's nests of cables. This will be cleaner in the final, when we're fully assembled. We're only part assembled now. And here's our completion of the focal plane. We actually got to this point about a year ago, so January of 2020. And here we are very happily putting in the last one of these units. So we took some images. You might have seen them in the press. We got a lot of publicity for this with the fully assembled focal plane. And we decided our normal test images are boring. They're flat fields or a grid of artificial stars. But we decided for publicity, we should do something more interesting. And so I invented a little thing I called a pinhole projector. It's basically a pinhole camera in reverse, where you have a light source here and a pinhole to project an image. That's a good choice, since you don't need any focusing. And once you have a pinhole projector, you can actually project whatever you want. One of the things we chose was this nice piece of fractal broccoli, a certain kind of broccoli. And that actually made for, so this is my colleague who could actually do the work because he's nimble enough to fit in this restricted volume. That's me. I'm a little bit too big to do more than work outside. In any case, it produced some what I thought were pretty cool images. So here's our Romanesco broccoli, and since you could image anything in the box, of that photograph of our namesake Vera Rubin, certainly an appropriate thing to take pictures. We took a couple others as well. Okay, those were for fun, and there were some interesting headlines. I think the BBC had a particularly interesting headline in their article about this, which I appreciate. Okay, so we have been doing some, a huge amount of testing of this full focal plane, optimizing its performance, studying how things work all together. All indications are the performance is going to be excellent. We're actually working to improve or solve a whole host of small but kind of annoying problems. Along the way, we make, we've been taking lots of calibration images. So I thought maybe you'd appreciate some of that kind of detail. This is read noise, gain from photon transfer. People are familiar with what that is, and dark current measurements. And actually, a lot of what you're seeing is not dark current. It's straight. It's a little bit of stray light from our projector and some calibration imperfections that we know about and are solving. So we're taking lots of test data so that the camera will really be ready when we're prepared to ship it to Chile. Now, course, there's more to the camera than the focal plane. I already showed you the optics. Here's some, maybe these are the same pictures. You've already seen the optics. Here's one of the filters. They're 80-centimeter filters, also no one has built filters of that size before. This is the I-band filter. You can see it kind of has an interesting color to it. We have a custom designed shutter. You can just barely see it here. These, you should be able to see it. You want it to have as little reflection as possible. But you can see its edges here. It's not easy to build because the beam covers such a big area that there isn't enough room for the blade of the filter to move off to the side without going outside our cylinder. You don't want to obstruct light, so that was part of the overall design, that everything in the camera would fit inside this cylinder. But it means we actually have double-bladed shutters, and those are a little bit complicated. The other difficulty is getting this filter in and out. At 80 centimeters, there's no room to put it laterally. So almost every other camera, kind of wide field camera, has a simple system for both the shutter and the filter exchanger. That's, if you can see my hands, it just goes sideways. So simple. We don't have that luxury. So the shutter's difficult. The filter exchanger is really difficult. And I don't have one of the videos that do it justice, but basically it has to move the filter. So this is the filter exchanger, and this is just a blank aluminum piece to represent a filter. It has to move it from being here to being sideways around the cryostat. So it has to move it 90 degrees out of the way. Very complicated. That was built by our partners at the Paris Observatory. And lastly, and these are pictures from just last month in the lab, here's the back cylinder of the camera that holds all of the support electronics, vacuum pumps, custom refrigeration equipment, etc. Small volume to do it. This is it. And this is only partially assembled. This will be more fully assembled in the next couple of months. Okay, that's my tour of the telescope and the camera. And maybe, actually, I want to wrap up in the next minute or two. Just a couple mentions of a couple other things. We have a whole effort in education and public outreach that's still being developed, but it will have elements strictly for education, especially K through 12 education, but also some books for citizen science projects. Space Warps is one of the Zooniverse citizen science projects. The observatory is, going to provide access for new citizen science projects to make use of Rubin Observatory data. There'll be a sky viewer to look in some way at the images themselves. And there'll be some form of notebook. This is a Jupyter notebook, if people are familiar with that, that will let the public look at some subset of the data more directly. That's still being developed. But I think in total, there'll be a number of interesting ways that interesting members of the public can look at the data from the Rubin Observatory. So I had a few other plots about, or slides about some of the non-dark energy science. Maybe I'll just focus on one of that, which, and I think actually, I've been thinking, what's it going to be like when we start taking observations? Dark energy is complicated. It will take some time to get results from the survey. Some of the earliest results will probably come from near-Earth objects. And this is an estimate of how many near-Earth objects there are as a function of size. And the red line is kind of an indication of what has been discovered. This is about 10 years old. I don't think it's changed too much since then. And the blue is what we think we could discover 90% of the objects out to this diameter. It's a log plot, so there's that's where the 6 million objects come from in here, or some fraction of the 6 million objects in the solar system come from. So I think some of the earliest science that will come out of Rubin Observatory are long lists of potentially killer asteroids. And that will be interesting to see. So with that, I want to stop. Just two mentions. So by way of conclusion, where are we now? Where are we going? This is a photo. It's from a drone, I think. Sort of an interesting angle where you can't see the support building, taken last month. And you can see the work on the dome is almost done. That's fantastic to see. And that will enable more work to happen inside the dome with the telescope mount. So things are moving ahead. Obviously, there was a big shutdown because of the pandemic, but work restarted some months ago. And for the camera, we are on schedule to be finished with construction and testing of the camera by the end of this calendar year. And we hope to be able to ship it thereafter. There is a mini camera, commissioning camera, of just one of those units, 9 CCDs. And there could be first light with that camera as early, probably not unofficially, probably not the end of this calendar year, but maybe the beginning of the next calendar year. We hope by the end of 2022 to have the full camera installed and working on the telescope, and the start of our 10-year survey to happen the following year. So with that, I thank you for your attention. I'll stop there.
Professor, thank you very much. A fascinating talk, and such a challenge both in the technology, the engineering, the electronics, and it'll be amazing when the science starts to come out. Perhaps we can show our appreciation. And Peter, perhaps you could call in the chats.
Yeah, great talk. Very, very interesting. Right, just I think Neil was the first on the list with Neil, would you like to ask your question? I think John had a go at answering it, but
yeah, thanks, Peter. Yeah, fascinating talk, Professor. My question's around the chicken or egg situation. So did you choose the observatory location first of all, or the hemisphere that you wanted to image first of all? And what was the reason behind the choice?
So that actually, I've been working on this project since 2010, and this decision was actually made about 5 years earlier. So there was a Northern Hemisphere site looked at. So there was a whole process doing site evaluation. There was some preference for Southern Hemisphere because it was thought there would be more interesting phenomena in the south than the north, but it could have been north. In the end, the site selection was down to this site and a site in Baja, Mexico. It was pretty close to the equator, but a little bit north. So a little bit north, and that was more of a greenfield site. Well, brownfield site maybe, since there's no green. And this site is a well-developed site. There are large telescopes there already and real infrastructure in Chile. So that was, I think, the deciding factor. But it was driven a lot by quality of the sightseeing, how many days of good observations could you get in a year, etc. So.
And John, you had a comment about our honorary president did some work on this, Andy Lawrence.
Yeah, what I was just going to say is Andy Lawrence is running one of the transient brokers for LSST or Vera Rubin's. It's actually available online. It's working on the Zwicky transient facility out there at the moment. It's only seeing about, I think it's 200,000 transients a day. But it then tries and filters, and at the moment it's sending me lots of alerts about fast-moving stars rather than anything else. It seems to have got a bit of an likes fast-moving stars for some reason. I've discovered all sorts of fast-moving stars I never knew existed.
I see. So, the Zwicky Transient Factory, and that is using the 48-inch Schmidt telescope at Palomar. And so it's looking at a much different range of flux than we do, right? So those are really bright objects. I think their depth is, they're limited at 18th or 19th magnitude. We can see 18th or 19th, we'll saturate at kind of 16th magnitude. Will saturate us, 15th or 16th, something like that. So, so we'll be looking in a different range. And I think actually, in terms of, let's go just. You know, in terms of stars, this slide says a little bit about what we'll be able to achieve. So fast-moving stars for proper motion. Well, so this isn't quite as fast as you're looking at, but what's interesting in this kind of science is that we're very complementary to Gaia, so the Gaia satellite, which, you know, doesn't really see much. I don't think they really get to 20th. Maybe it's more like 19th if I remember right. But they do extremely good measurements of parallax and proper motion in that range, but they can't see anything below it. We won't have the kind of accuracy they have in that region because we don't see the objects enough times. And our individual measurement errors in position are worse, a little bit worse. But we'll see a whole host of objects that Gaia can't see or that Zwicky can't see at these depths. And that will let us map out an enormous new part of the Milky Way. So.
Excellent. Very good. Carl, you had a question? You're on mute, Carl.
Thank you. Sorry, thank you, Professor. I really enjoyed that talk. I was interested how your camera is going to be affected by low Earth satellites. I mean, from what I hear at the moment, there's going to be thousands and thousands of things. So how are you going to are they going to affect your imaging?
Yes, yes, they will. Yes, they will. So let's see, let me stop sharing to go backwards. So if let's look, maybe here's the best spot. So they will, and we've, you know, you may have seen the image that comes from the dark energy camera that shows, you know, a dozen or so Starlink satellites going across their field of view. Actually, I'm also a member of the Dark Energy Survey. I was involved in the construction of the dark energy camera as well. So we've looked at the expected brightness of those, especially Starlink. Most of the work has been done with Starlink, that's SpaceX constellation. You know, those will look like between 5th and 7th magnitude objects moving across. You know, certainly when you see them, you know, they're easy to find, no problem there. You have to block out a whole swath of the sky, a line across the focal plane that's unusable. We know that piece, that is a nuisance. Now, you know, there are satellites already, so you see satellites, they're not as bright as those, many of them, but you'll see them, you have to mask them out. What we're worried about is, and especially because we have 16 channels per CCD, there's crosstalk from one amplifier, one section of CCD to the neighbor. That's something that will be characterized well. But what we're concerned about is how many different sort of shadow, you know, or crosstalk-induced streaks will there be across the focal plane? And can we correct those well enough to be able to use that part of the imaging? Now, there's still an effect because you've got some signal you have to subtract, so you always do a bit worse. That's where our biggest concern is there's a multiplier. So it might not be just one streak, but there may be these extra crosstalk streaks. You know, if the full constellation of tens of thousands of these satellites is put up, it will put a very significant crimp on our imaging in terms of how much real estate on the sky we lose. It's significant.
Okay, thank you very much for that.
Thank you. Sorry, I clicked the wrong button. Thank you very much, Professor. Thank you.
Mark, do you have YouTube questions?
Will, up to Will, I think.
I can, we can say a couple here. So first of all, we've got from Pat Bowman. Are any adaptive optics being used to maintain quality seeing?
Okay, so the answer is no, not adaptive optics. So you have to remember that adaptive optics systems can only work over a very small part of the sky. So a typical coherence angle for an adaptive optics system is of order arc seconds. 5 arc seconds, 10 arc seconds. Systems that, I mean, you have to take even more steps to get up to an arc minute, and typically only ground layer seeing is corrected at that scale of, arc minute or several arc minutes. So, and the reason is actually easy to understand. Turbulence, it's a random phenomenon in the atmosphere. So in adaptive optics, you're correcting for the atmospheric turbulence on time scales like a millisecond. So you need to do the corrections at a kilohertz. If you think about the beam, so you have to look at my hands for this. If you think about the beam from the telescope going in any one direction, that's like an 8.4 meter diameter cylinder through the atmosphere. And if you're looking at an object in one direction versus an object at a little bit different direction, those cylinders through the atmosphere are different. So it's a different turbulence pattern you see. So you can't correct from one place to another. You can only do the correction over a tiny angle. We have a giant angle. We're 3.5 degrees across the sky, so there's no hope. What we do instead of adaptive optics, we use what's called active optics, and that's slow correction. That instead of operating at a kilohertz, goes at a correction per minute. And unfortunately, this doesn't show it, but in the corners, I mentioned that there's a wavefront sensor. So basically, it's just another CCD that's broken in two, that's got two halves. One half is above the focal plane, the other half below. In each image we take, we see out of focus stars in those wavefront sensors. And we can use the size and shape of the out of focus star to measure the optical wavefront and to learn about whether we're in focus, a little bit out of focus and a little bit out of collimation. And so in between images, we will correct those things because we have a hexapod on the camera, we have a hexapod on the secondary mirror, and we have actuators in the primary mirror, tertiary mirror, and the secondary mirror. And so kind of at a slow cadence, we will adjust all of those to maintain good mirror figure, good collimation and alignment, and good focus. So for amateur astronomers, if you're familiar with what's called the STAR test, what we're doing is basically similar to that. Obviously souped up, much more sophisticated.
Excellent, thank you, Prof. And just have one more from Ming Yang. I think you answered this in the last slide, but just to get it straight from you, sort of what do you estimate the commissioning, length of commissioning time for the LST, realistically?
So we had hoped for a full year of commissioning, and I think that's been pared back to half a year of sort of on-sky commissioning. People call it these days science verification. So but we still anticipate around a 6-month period where we'd be both getting the instrument, getting the telescope and camera to work perfectly together, and taking images and doing mini surveys to sort of study the whole observatory from soup to nuts to make sure we're working. So we'll still have a 6-month period of that.
Excellent. That's questions from YouTube. Thank you, YouTube.
Well, can I say, Professor, thank you very much for giving your time up. We really appreciate that we're not a large organisation, although our reach is growing ever wider. We really appreciate you taking the time out to give us the talk. Absolutely fascinating. And we'll certainly be watching things progress. Perhaps we could show our appreciation.
My pleasure.
Thank you very much indeed. And we will be sending a small gift as a token of appreciation. It won't worry the IRS. You can be assured.
Thank you. Everyone take care. Bye-bye.
Okay, Mark. We're going now to Alan now for a presentation on the sky in January, and a cold sky it is too.
It is. Yes, hi. About to try to share my screen. Right. Can you see that?
Yes.
Yep.
Right. Happy New Year, everyone. As Andrew says, it's cold. This background image is a nice image of the Elephant's Trunk Nebula taken by Ian Smith. I'm going to come back to that image a little while. The usual two-hemisphere star charts for January, valid for these times, showing the northern sky and the southern sky. I always point out the plough, and it's now starting to climb in the northeastern sky at these mid-evening times. Across the pole star Polaris is Cassiopeia, the W or M of Cassiopeia, and we've already missed, or perhaps you've seen, the Quadrantins meteor shower, which has its radiant not far away from the plough. The only bright planet in the sky at these times is Mars, which is now in the evening, still bright but fading and getting smaller. And of course, the main attraction this month is Orion, the center of a sparkling region of bright stars and constellations. And I'll come back to talk about that more later. Let's begin with the sun and the moon. This is the ephemeris for the sun, taken from Dominic Ford's inthesky.org website. The sun is now moving northwards, so the days are getting longer, thankfully, 90 minutes longer for us in Edinburgh during January. And the Earth reaches perihelion.
Oh, that's fine.
The closest point to the sun in its annual orbit on the 2nd of January, so we've passed that point now, when we were 147 million kilometers from the sun, which is 5 million kilometers closer to the sun than we will be at aphelion, the farthest point from the sun in July. And the moon's phases for the month, we're now entering the dark of the moon. We're into this region when the period of time around the moon being new moon is still a morning object, a last quarter object, and a waning crescent in the pre-dawn sky. And then we have new moon, and by January 20th, we're back to the moon at first quarter, and the nights get a bit lighter. The planets in January, also from Dominic's Ford website. This is the sky stretched out around the equator. The sun is down here, just past its most southerly point. The yellow line is the ecliptic, the sun's apparent path through the night sky, through the sky each year. The sun's here. It's moving obviously eastwards. The arrow shows its motion during the month, so it's climbing northwards. But you'll notice that there aren't a great many bright planets visible along this line. One of them is Mars, which is, as I say, getting fainter and smaller through a telescope. We're losing Venus, which is slipping into the morning twilight. It's very low in the southeast before dawn. Jupiter and Saturn, as you know, are now disappearing into the evening twilight following their great conjunction. You'd need a very clear weather and an unobstructed southwestern horizon to see them now. Both pass around the sun's far side later this month. One planet that does become visible this month is Mercury, which has an evening apparition. It passes Jupiter and Saturn as it emerges from the evening twilight, and that's low down in the southwest. Before I go on to talk about the coming month more, I'll mention this great conjunction that we had. Fran Goodman took this lovely image of Jupiter and Saturn. There they are right in the middle, Saturn above Jupiter, on December the 20th, the day before the conjunction occurred. I took a view from Fair Mile Head, so I caught the two planets, Jupiter and Saturn, just before they dipped beyond the Pentlands and above some power lines. But Will Joy got a much better view on that night. I think the 21st, the day of the conjunction, was poor weather for us. But there you can see Saturn and its rings and Jupiter to the south of it. Let's come on to how those two planets faring at the moment. On January the 1st, they were still visible in the evening sky. By January the 10th, they're getting a good deal lower down. These views are for 30 minutes after sunset in the evening, and you'll see Mercury coming up below Jupiter and Saturn. So by the 14th, Mercury stands above Jupiter, above and to the left of Jupiter and Saturn, and to the left, Mercury stands to the right of the moon. Now the moon on that night is 3% sunlit, a very fine crescent, 5 degrees to the left of Mercury. Mercury is at greatest elongation from the sun when it stands furthest away from the sun in the sky on the 24th, which is here, and it draws, and after that it draws closer to the sun. It also gets fainter. Those are its appearance on January 10th as it's passing below Jupiter and Saturn. It's magnitude minus 0.9. It stays in negative magnitudes for most of this period, but by the end of the month and beginning of February, it's down to magnitude 1.1, and we're certainly losing it in the bright evening twilight. Now back to that Elephant's Trunk Nebula by Ian. This is the trunk, the Elephant's Trunk as it's called. It's a region of cooler gas and dust in which, in a much larger cloud of ionized gas, that's the pink glow you see all around. And the clouds, the darker, cooler clouds are being eaten into by radiation from ultraviolet radiation from surrounding stars, particularly a massive young star over here. And the edge of the trunk is glowing pink. And inside this trunk, the material, the gas and dust, mainly hydrogen, of course, is condensing. And right where I've got the point, the cursor there, the laser there, a couple of new stars formed. They're very, very young stars. So new stars are being created, new planets are being created in the Elephant's Trunk Nebula. Let's take a tour of the night sky and look north. This is the view north from Edinburgh at 20 hours, 8 p.m. on January the 16th. The Elephant's Trunk Nebula is here in the southern part of Cephus. The king, Cassiopeia, is the queen. They are mythical king and queen of what we call today Ethiopia. Beginning to climb in the northeast is the plough. There's Cassiopeia, which is overhead at nightfall, but then falling down to what in the northwest as the night goes on. Now, the Quadrantids meteor shower has its radiant point, the point in the sky from which the meteors diverge, not far away from the handle of the plough, low down in the north at these times in the evening, but climbing up through the northeast overnight. And that's the view at 6 o'clock in the morning on January the 3rd, when we probably could see quite a few meters if it had been clear. The plough at that time is overhead. You can just see the handle of the plough. The overhead point is up here at the top of the diagram. The handle of the plough, arc to Arcturus, the bright star in Boötes, and then onwards to Spica. Meteors are in all parts of the sky, not just around the radiant. The details for the Quadrantids are there. The shower lasts till January the 12th, so we'll still see a few, if you look carefully on a clear night, emanating from this region. But the peak was really due at 11 o'clock GMT in our daylight on January the 3rd, when the zenithal hourly rate was 80 or more, which is the rate you would a single person would see under a perfectly dark sky. They are medium speed meteors. The peak on that day was quite narrow, and as I've mentioned, there is some morning moonlight, but there's still a few stragglers around until the 12th. This is the view looking west at those mid-evening times. This indicates that when this chart is valid, it's valid for 8 p.m. on January the 16th. On the 1st of January, it was 9 p.m. and by the month's end, it's 7 p.m. GMT, and it's still valid. The stars are in the same position, but moving objects like Mars will not be where it's plotted on this diagram. The summer triangle is no longer visible, although we still see Vega and Deneb in the northwest. The whole of the triangle, though, does pass below the pole in the north, and the whole of the triangle is visible, becoming visible before dawn. The square of Pegasus is more or less due west, Andromeda leading up from its top star, and of course M31, the great galaxy in Andromeda, is visible, still fairly high in the sky, in the evening sky. And Mars is in the southwest. And if we look south, better view of Mars, to the south of the star Hammel, in the brightest star in Aries. During this month, Mars moves 15 degrees eastwards from Pisces into Aries. And there are its details again for the beginning of the month and the beginning of February. So you see the size of the planet is shrinking. It's only 8 arcseconds or 7.8 arcseconds wide by February the 1st. So it's getting a bit small for telescopic study, and you'll be hard pressed to see detail or photograph detail on its surface. It's also now dropping below magnitude 0, the brightness of the brighter stars like Capella, which is nearing the zenith at these times, and Vega. It's also passing north of the distant planet Uranus. In fact, that's Stellarium's view of the path of Mars relative to Uranus. Uranus is also moving, but its motion is too small to show up in this diagram as Mars moves to the south of the star Hammel. So at the moment it's around here, but by the end of the month it'll be 15 degrees along its track. This conjunction, of course, is not so impressive as the one we had recently between Jupiter and Saturn. And those are the relative positions at mid-month on the 16th of January of relative sizes of Mars and of Uranus. Uranus is only 3.6 arcseconds across, magnitude 5.7, quite easily visible through binoculars, so you can use Mars as a guide to finding Uranus if you've never seen it before. If we look south, if we can, sorry, we're still looking south. I want to focus on the constellation of Taurus, the bull, which lies to the east of Mars at the moment. This is the view from Stellarium of Taurus. One star of interest in Taurus is Lambda Tauri, which is an eclipsing variable star similar to the star Algol in Perseus. It varies in brightness between magnitude 3.4 and 3.9, and it was the third such eclipsing variable star to be discovered. The stars, it consists of 2 stars, which revolve in just under 4 days and are separated by 0.1 of an astronomical unit, the distance, 0.1 of the distance between the Earth and the Sun, or about 11 times the Sun's diameter. During eclipses of the brighter star by the fainter one, the total brightness drops by around 50%, and Lambda Tauri lies around 480 light years away. Of course, a favorite object in Taurus is the Pleiades. Another Ian Smith photograph showing the Pleiades, the 7 sisters, 440 light years away. The stars there are 100 million years old, and they're embedded, or they're passing through a cloud of gas and dust in our galaxy. So they're lighting up some material that happens to be on their track through our galaxy. This is not the remains of the material from which they formed. Also here are the Hyades, the V-shaped Hyades star cluster. It's an older cluster, 625 million years old, but it's about a third the distance from the Pleiades are. It's only 153 light years away. Aldebaran, the brightest star in the Hyades, this one is an orange giant star, 65 light years away. So it's a foreground object compared with the Hyades cluster beyond it. Telescope users know that the first object in Messier catalogue M1 lies near the southern horn of the constellation Taurus. It's approximately 6,500 light years away, visible through binoculars just as a very faint magnitude 8.4 star, which is the slightest bit fuzzy, but it's a debris of a supernova explosion which was observed by Chinese astronomers back in 1054. The neutron star at the center of the Crab Nebula, there's an image of it by Mark Phillips. The neutron star at the center of the Crab Nebula is around 30 kilometers across, and it spins on its axis 30 times a second. And it's emitting radiation at all wavelengths, from gamma rays to radio waves, including light. It's a bit like a spinning lighthouse. You don't get many lighthouses spinning 30 times a second, though. And turning to another area in our southern sky, above Taurus is the constellation of Auriga. This is Auriga again in a stellarium view. Elnath is this star here, is the northern horn of Taurus. It actually belongs to the constellation Taurus, but many diagrams show it joining up with the stars of Auriga as though they've got dual nationality. In this case, it's a bit like Alpheratz in Andromeda, which often is taken as part of the square, of Pegasus, and the two constellations are joined by Alpheratz. For now, I want to point out 3 open star clusters, which are good to look at through telescopes. You can also see them in binoculars. They're much more distant relatives of the Hyades and the Pleiades. M38 here is the fainter of the 3. It's about magnitude 7.4. It's 3,500 light years away. And it's around 2/3 of the size of the moon in the sky and 290 million years old. M36 is to the south and east of M38. That's an image on WikiSky. This is only, the stars here are only about 25 million years old, and the cluster is only about 10 arc minutes across, so 1/3 the size of the moon in the sky. And it's very similar to what we would see if we saw the Pleiades at the same distance of 4,300 light years. M37, the most southeasterly of the 3 clusters, is shown here. It's 24 arc minutes across and 350 to 550 million years old. The stars there, the cluster is that old. A way to find these 3 clusters is to take a line from Elnath to Mahasim, which is this star in Auriga, and about halfway along that line and at right angles to it is the line of the 3 clusters. So that's one way to try to find them. Turning east in the middle of the evening, this is the view. Orion in the southeast, Gemini coming up in more or less due east, below the Bright Star Capella, and there's the Plough in the northeast. A couple of hours later, this is the view looking south as Sirius, the brightest star in our night sky, passes more or less due south. Orion is standing upright in the south, below Taurus and below and to the right of Gemini. I want to focus on this area of Orion. Here is the stellarium view. As you know, the Orion's belt slants upwards to point towards Aldebaran and the Hyades and onwards to the Pleiades. If you take the line the other way, then it points down to Sirius. I'd also like to point out the prominent triangle formed by these 3 stars, Betelgeuse, Procyon, and Sirius. We call that the winter triangle to distinguish it from the southern triangle. The 2 triangles are around 180 degrees around the sky. So when one's in the south, the other one is below the pole in the north. Incidentally, there's no evidence really that Betelgeuse has been fading again since its big dip in brightness of about a year ago. Back a year ago, some people were speculating that Betelgeuse would be about to go supernova. But for the last 4 or 5 months, Betelgeuse has been pretty steady in brightness at about magnitude 0.7. So it's not showing any evidence of doing anything naughty. Now let's focus in a bit more on Orion itself. This is Stellarium's closer up view. The head of Orion is up here. It's not so bright as the other corner stars of Orion. It's actually a star cluster, the Lambda Orionis star cluster, or sometimes called Colander 69. That star cluster is around 1,300 light years away. If you take a line from the head of Orion through Betelgeuse and then continue it to the next brightish star you come to, magnitude 4.4 star, which is in Monocerotis, the constellation, then and if you again take a slight turn and go due east for 2 degrees, which is 2/3 the length of Orion's belt, you get to, I think you can see it on this diagram, a sort of pinkish glow. That is the Rosette Nebula. What you can see in binoculars is a star cluster at its center, the star cluster NGC 2244. But if you take a long exposure, time exposure of the nebula, this is the beautiful view you get. This is Nigel Goodman's, another ASC member, photograph of the Rosette Nebula. The star cluster there is a very young one. It's only about 5 million years old. And the Rosette Nebula and the star cluster are around 5,000 light years away. And the cluster has around 2,500 young stars, and there is star formation ongoing inside the nebula. And there's a sort of hole in the middle of the nebula blown by radiation from the largest stars. And a thing I've noticed recently is that this nebula is the official state astronomical object for Oklahoma. Apparently, they were interested in encouraging their dark skies for astronomy, and so they have I think it's the only state to have an official state astronomical object. Maybe Scotland could think of something to have as our national astronomical object. Again, I'm going to focus in on to a part of Orion now, this region here, the belt and the sword of Orion. That's a photograph by Greg Loudon of the Orion's belt and sword. Here are the 3 stars of Orion's belt. This is the sword of Orion. And this is a recent photograph by Mark Phillips of that region, showing the Orion Nebula, Messier 42, and the Running Man Nebula, NGC 1977. The Orion Nebula is about 1,350 light years away, and it's the closest region of massive star formation in our sky. Appears fuzzy to the naked eye, and it's obvious through binoculars. 24 light years across, and there's a young, right at the center there is a young star cluster, the Trapezium. The Running Man up here, you can just see, is a darker region seen in profile against the glowing reflection nebula. But you can't really see the naked Running Man through binoculars. You need only in photographs does it show up at all. A region around Alnitak, which is the left hand of the 3 stars of Orion, was photographed quite recently by Andrew Farrow. There's Alnitak, and this is the Flame Nebula. I think you'll agree it looks like a burning torch, if you like, with a dark obscuring region. The dark lanes are gas and dust in front of a brighter nebula. And to the south of that, here is the Horsehead Nebula, Ian Smith's image of the Horsehead Nebula, a darker nebula seen in profile against some glowing hydrogen gas. This was first recorded in 1888 by the Scottish astronomer Williamina Fleming, who had emigrated to the USA at the age of 21. And within a couple of years of getting married, she was already divorced or separated from her husband, and she joined the household of Edward Pickering, who was the director of the Harvard College Observatory. She joined the household there as a maid before her skills were recognized, and it led to her being employed at the observatory and taking on work to catalog stars and analyze the spectra. And she was the first one to record the Horsehead Nebula. And she discovered lots of nebulae, in fact, variable stars too, and novae, and also the first white dwarf. She was the discoverer of the first white dwarf spotted in the sky. It's a companion to the 4th magnitude star, 40 Eridani, which is 15 degrees west of Rigel. So it's in the same part of our southern sky, and 17 light years away. Mark Phillips has produced this montage of images of M42 taken over the last 10 years through a variety of telescopes and cameras and filters. But that's a terrific effort there on the Orion Nebula. And finally, I want to mention Venus, because that's slipping into our dawn twilight. This is the view on January the 1st, when Venus rose only 90 minutes before the sun, and it was brilliant at magnitude minus 3.9. This is, as you see, 30 minutes before sunrise on these dates. By January the 11th, it was down rather lower, and it rises only 63 minutes before the sun. But on that morning of January the 11th, it's met by the moon. The moon's less than 7 degrees to its right, to its left rather, and the moon is 5% illuminated. The details for Venus at the middle of the month are there. It doesn't really change in size or appearance during the month, but it does get lower. By the 31st of January, it's just 15 minutes. So it rises just 15 minutes before the sun as it slips towards the sun's far side. In fact, it doesn't reach superior conjunction, the far side of the sun. It doesn't reach there until March the 26th. And we probably won't see it again until it emerges in our evening sky a month or two later. And it'll be low down in our evening sky right through until the end of the year. And that's all I've got for you this month. Thanks.